inform you that it will be the same link for the next part of the conference tomorrow morning. So same Teams link for tomorrow. So good to see you, Payam.
It's a pleasure. Thank you, Monica.
So please introduce yourself.
Certainly. My name is Payam Pourmand. So I did my PhD at the Royal Institute of Technology, KTH. And I'm currently living in London, and I'm working here mostly in the mooring business, in the floating offshore wind business. But in parallel, I'm also working with KTH more or less on anything which is related to polymer degradation and stability, and also this recent project that we had on a development of an NMR sensor for cables.
Thank you.
So I'm just going to share my screen. Just a second. Can you see my screen?
Yes, thank you.
Brilliant. So today's talk essentially is going to be about polymer degradation in nuclear applications, but I'm probably going to lean in more to nuclear magnetic resonance and how we've used that for essentially to evaluate cables. But I wanted to give you guys first an overview of polymers used in nuclear applications, and then lean into the cable side of the story. So I guess it's quite well known for everyone in today's presentation that there's a lot of polymers which are being used in nuclear power plants, and they have a very vital functionality. But I think the holy grail of all questions for all of us is how can we predict the functionality and also the lifetime of these components, essentially to make proper integrity management strategies and intervene when necessary. So there's a lot of materials. So just an example is 1,100 kilometers of cable in one reactor. So there's a lot of responsibility and a lot of need here, especially as the nuclear power plants are being pushed for further extension of their lifetimes. Well, accelerated aging, a good question is why are we doing it? So essentially, most of the components that we are using, either they can be in harsh conditions, but most of them are in rather mild conditions, I would say 30 degrees Celsius, 25 degrees Celsius or in room temperature. And it's quite difficult for us as scientists to try to mimic experimental times that can be very long, for instance, like 30 years of operation. So we are really in the need of doing accelerated tests. And usually when we do accelerated aging tests, we base them very much on the assumption that when we do a high temperature aging or a high dose rate aging, we assume that the degradation mechanism at those extreme conditions are more or less the same as the operational conditions. But you have to take that with a slight pinch of salt. And I think that, as Anya showed also in her slides, at high temperatures, you can get other phenomena, for instance, the diffusion limited of oxidation. So when you do accelerated aging, it's really evident that you need to plan your experiments and try to tune your experiments so that you're mimicking more or less the conditions and the boundaries of the application. But at the same time, you still need to have tools, essentially profiling tools, where you can assess your material and try to see at these high temperatures or high dose rates, how has the material actually changed and been altered. So profiling methods is possibly, I would say, one of the major things I did in my PhD. So I've profiled a lot of different things, and I think these blocks are these cable insert blocks from MCT Brattberg. They're still haunting me every night, but they still exist on my head. So we did a lot of profiling during my PhD work, and some examples of profiling work is essentially in the intermodulus, which also Anya showed, where you're looking at the surface hardness of your sample, or you have, for instance, infrared spectroscopy, where you're looking at the carbonyls. So the carbonyls are essentially a oxidation residue that you get from polymer oxidation. And we also have a portable NMR, which I will talk about briefly, and give you guys a bit of background and also some know-how about. And we also have extraction profiles that people do. So they essentially try to understand at different levels through the cross-section of the sample how much oil extender or low molecular components that have actually left the sample. The image you guys see here to the right is essentially a cross section of one of these cable transit seals. So I just wanted to show this image that when you do a high temperature aging, you get this non-homogeneous oxidation. So you get a lot more oxidation at the surface compared to the bulk. So you get this indifferences. So that's why when you do these accelerated aging tests, you need to have mechanisms and tools where you can actually try to understand what's actually happening in your material and try to assess what is actually mimicking the reality mostly. So with regards to profiling methods, it's, I would say, when it comes to sealants and blocks, I would say it's quite straightforward. But during the course of my PhD work, there was a major question which popped up from my colleagues at the nuclear power plants was, how about cables? Is it possible to profile cables, or is there a non-destructive test method for cables? So during the PhD work that I was involved in, we did a lot of portable NMR profiling, and we started to think back then about cables. So a side project which started off from that PhD was a funding from SSM, where we looked at essentially to develop a sensor to measure on cables. Cables is a science for itself, I would say. There's tremendous amounts of different type of cables in the nuclear power plants, and the question we had from some people were essentially the primary insulation. How can you measure on that? How can you understand how's the degradation in that component? So it's a very tricky component, I would say, cables. But at the same time, we felt that we should give it a shot and try with our NMR sensor. So just quickly about some traditional testing methods when we talk about cables. I know that one of our colleagues is going to talk about that also after this, presumably. So when we talk about cables, essentially a lot of mechanical testing, like strain at break testing or surface hardness testing. So it's mostly the type of evaluation where you have to go out to the cable, cut it off, take it to the lab, evaluate it, or if you're lucky, you can do an indenter measurement on site. So when we were thinking about this NMR sensor for cables, we had two questions for ourselves. The first one, can we make a proof of concept where we can make a prototype which can function for cables? And number two, can we come up with a design which we can use for the operators to use in the field? So essentially something to make life easier for those guys. So that was the basis that we had essentially. So before I jump into the sensor and all the functionality, just to give you guys a feeling of how NMR works in the NMR application that we used. So the NMR application that we've been using is the low field NMR. So it's not like the high field NMR that you've probably seen in some chemical laboratories where you can essentially get a spectra and understand which constituents you have in your sample. Or it's not like the magnetic imaging camera that you have in hospitals. So the magnetic field strengths are far smaller. And because of this limitation of the magnetic field strengths, it essentially limits us to work on the relaxations of protons which you have in your sample. So the reason that we are interested in relaxation times, especially the transverse relaxation time, the T2, is essentially because T2 is very sensitive to molecular mobility. So when you have a polymer which is being aged and it's cross-linking and you're losing, let's say, even oil extenders from your materials, so it's another form of degradation, you can actually detect that with the transverse relaxation with the T2 values. So essentially, as you age your material, as you're cross-linking it and it becomes more and more stiff, it's going to affect your T2. So you're going to get a shorter T2 as you age your material. So it goes really well hand in hand with aging, I would say, the transverse relaxation times, and it gives you a good indication of if your material is actually aging. The image you guys see to the right is a schematic of NMR mouse. So it's a commercial name, the mouse, but essentially it's a low field NMR sensor. the functionality of this sensor is, it's a lot of physics behind it, but the easy explanation, at least from a side of a chemist like me, is that this is this stand essentially that we have, and then we have an elevator device, so to say. And on this elevator device, we have a permanent magnet. And what happens is that when you have this permanent magnet, you're going to have a magnetic field which is more or less always constantly around the magnet. So it's quite straightforward. And on top of the stand, we place the sample. So this gray image you see here is the sample. And what we do simply is that inside this magnet, we have a coil. And what we do with that coil is that we introduce a current. And the reason that we do that is that we want to create another magnetic field. So what we do is that this sample, which is on the sample holder, so essentially the protons. So if you imagine the protons here at this location, which is 5 millimeters from the surface, they are all in the direction of equilibrium, I would say. And as we induce a current through that coil, we're going to create a magnetic field which is perpendicular to that external magnetic field from the magnet. So we're going to push the protons essentially out of equilibrium. And when we cut off the current, these protons are going to relax back to the equilibrium position. And essentially the time of relaxation is the transverse relaxation time that we're looking for. So essentially what we do in NMR is that we use this manipulation of the magnetic field to create something that we call a sensitive volume. So it's a 120 micrometers surface area. So it's a very small, thin area, which is 5 millimeters above the magnet. So we create that volume of measurement. And with the help of this elevator device, we can essentially travel up and down and then screen through the sample. This is just a quick image of some commercial devices which are in the market. These images are rather old, but there are a lot more newer ones, more advanced ones, and these are actually quite widely used in qualifications now and also in quality areas. So the tire industry, Pirelli is using this daily. Audi and the car manufacturers and the auto industry are using this. And we are actually starting to use this now in floating offshore wind. So when we make these massive synthetic fiber ropes, one of the screening methods that we have is essentially to check with NMR to find any form of deformalities or any form of changes in the material. So these are again from my old thesis, just to show you guys how we did some profiling with the NMR. So the image to the left is an indenter modulus profile. So this is the surface hardness, and this is the distance from the surface. So the surface is essentially here, and this is 5 millimeters in, and this is the image of the block that we have screened. So as you can see from this surface hardness, you see that because of the high temperature aging, we have a lot more oxidation at the surface compared to the bulk. And if we look at the NMR, we see the same pattern, but it's flipped. So we see that at the surface, we have far less relaxation times. So the relaxation times are shorter. So it means that the material is stiffer compared to the bulk. So we haven't still yet done a full quantification of relaxation time to mechanical behavior, but it's still in the phase of the trends are the same. But the future research definitely should be that we should try to quantify relaxation more with mechanical data. Since one thing which is totally widely accepted in the nuclear industry is mechanical testing. So a breaking load test or a stiffness test is widely more accepted in the industry. So we need to start to benchmark relaxation times more to that. So when we started off with the cables, the first idea we had that, okay, we have some cables. Can we use the NMR mouse that we have in the lab? Can we get the signal even with that? So the trouble with cables is that compared to polymeric sealants or blocks, where you just essentially have, it's just a rubber, you have some filling materials. It's a rather simple medium, I would say. With cables, you have shielding material, you have the insulators, you have a lot of different constituents which can actually alter your signal verifications. So what we did was that we quickly test it on the NMR mouse to try to see does it work. So the image to the left is essentially a cable insulation where we simply took out every form of steel component from it and just kept the polymers and primarily the cable insulation, which was of interest. So we saw that, okay, fine, we can get a signal from the polymer without any form of interference from any steel. The image to the right is when you don't do anything at all with the cable. You just simply put the cable on top of the sensor and you actually see that you're not getting much. So we were actually scratching our heads and we were saying, okay, fine, this commercial single-sided sensor is not going to work. And what I mean a single-sided sensor is essentially that you have just the magnetic field strength in one direction. So it's yeah. And what we started to brainstorm about was that, okay, how can we enhance the magnetic field strength to start to slice through a cable? So we started to do a series of simulations in COMSOL. And one of the simulations that we did was essentially on arrangement of magnetic of the permanent magnets to get the maximum highest magnetic field strength in the center. So the image you see to the left is essentially a constellation which we call is a Halbach array. And by placing these magnets in a certain array like this, you can actually maximize your magnetic field strength in the center. So we did a series of simulations to establish of which configuration of Halbach is going to yield us the highest field strength. And in parallel to that, we also developed some RF coils, essentially the conducting material, to try to establish, okay, how can we tune frequencies and how can we develop this essentially to try to slice through a cable. So we made a prototype and preliminary, it works, I would say. Just to be very clear with everyone, now this prototype and the whole project, the aim here was essentially try to, can we make a sensor that can scan a cable? So we didn't really dive into making a DOE of cables, of looking at temperature, radiation dose rates, or the past history of cables, nothing like that. We were just looking at proof of concept. Can we actually make a device which can work on a cable? So right now, this is a prototype which is really low in TRL level, but this is essentially the permanent magnet, and this is the RF coil that is placed here. And there's a hole here. You can unfortunately not see it in this image, but we placed the cable through it. So this prototype currently now is a destructive way of testing cables. So we need to cut cables off and put them through here. But one of the designs that we have developed is essentially, it looks like a horseshoe. So it's two horseshoes that you can just connect together and just put around a cable and then try to measure. And the idea of that was essentially to have something for the operators to use in the field. But that's something we hope to do in the future. So these are some of the constituents of the sensor. So these are the RF coils that we made in the lab in KTH. And these are the magnetic Halbach arrays. So you can actually see from these arrows where it shows essentially the direction of the field strengths. So by putting them together into this constellation, we are able to create the highest magnetic flux in the center. So Ringhals and Forsmark, the team there, they were really helpful. Every time we needed something, they always supported us. So we got some samples from both these nuclear power plants. As I mentioned, the aim here was mostly just to get cables which are more widely used in the nuclear power plants, just to have something to test on. So we haven't gone really dived into like the past history of these cables or looked at, for instance, their exposure times. And sometimes the data of some of these components has not been there. So essentially, we just got some samples and no past history, unfortunately. But this is something that we need to dive into and look into for future studies. So we had these cables from the nuclear power plants, and this is some of the data that we acquired. So this is essentially the transverse relaxation times, is the T2. As I mentioned, a low T2, so this is 0 here, means that you have a very stiff material, so you don't have so much mobility in your material, compared to high T2 means that you have higher mobility. And this is plotted to the strain at break. So the two data points that we have here, essentially the green one, reference unaged, is a polymer which has not been aged, doesn't contain any steel components or any ferromagnetic components, so it's just pure rubber. And this other component is the EPDM, so that's also an EPDM, I apologize. So it's an EPDM which has been aged at 170 at 100 hours. And the reason that I put these out is that I wanted to show that these are the cable data that we acquired, and these are the non-cable data. So you actually can see that it's a rather big influence from the cable constructions and also these ferromagnetic components that can affect the NMR sensor compared to the more traditional polymer samples that exist. But when we look at the data more closely, we can clearly see that these two data points, R9 and R12, are essentially cables which are new. They haven't been aged. And if you put them into the context of these other samples which have been in use, we can see that there is an indifference in relaxation time between the new and the used cables. So just to point out, this is the cable insulation material that we've managed to measure. So what we've done is that we've known the cable dimension, and by tuning the RF frequencies, we are able to measure at a certain point inside the cable. So we measured essentially the cable insulation. And this was a quite tiresome job also that we had for the mechanical testing. So we had to cut out these pieces of cable insulation and do some strain at break testing just to get a feeling of where in relation they are. This is some Young's modulus data. So again, we see the same trend here. So as I mentioned earlier, much higher signal for the pure rubber samples, reference sample of cable, still giving you a higher T2 time, lower modulus compared to these these samples which have been in the field. So preliminary, we are seeing something positive here, I would say, but we are still really, really low in TRL, so we need to do a lot more. Just to conclude about our findings, I think one thing which is quite unique with this study is that we've developed essentially a sensor which has a much higher magnetic field strength compared to the more commercial sensors which are available. And we can see that the sensor works on certain cable types. So the challenge here is mostly that when you have cables where you have a lot of steel shielding or mechanical shielding, which is giving the cable essentially mechanical integrity, and if it's ferromagnetic, it can actually alter the signals a lot. So those are the type of cables that we struggle with. But cable types which are, I would say, more polymeric and not so much steel involved in it, besides the conductor, those are more straightforward to analyze with the sensor that we have. As I also mentioned, the transverse relaxation times that we are measuring with the cable, with this device, they're rather short compared to ordinary polymers that we've been working with before. So we've essentially devised a way of quickly, based on the curves that we acquire, to analyze what is the age polymer contribution, what is essentially from the oil extender in the polymer. So we can quickly just single out what is what from the data. And the final thing I had to say was to thank the whole team who's been involved in this. First of all, to the Swedish Radiation Authority for supporting this project, and also for Elena Kalota for always supporting us in this project. And also for the Vattenfall team, they've always been helpful, always been there for us when we needed something. So Josef in Ringhals and Abu Rahme also in Forsmark. And finally, also the KTH team. So Professor Istvan Furo and Pavel Yushmanov from the Department of Physical Chemistry, and the team of Mikael Hedingqvist in Polymeric Materials. Now, I know that this has been a lot of information for you all to grasp, especially in just 20 minutes to give you an update about a sensor like this. So there is a full report down in this link, which is on the SSM website. So if you guys are interested, you could carry on reading that. And if you have any queries, just give me a shout. I'd be glad to help. Thank you so much.
Thank you very much, Payam. It's always very nice to see something that's very hands-on, I think. And as you know, we always appreciate different kinds of non-destructive techniques to measure our components. So what is really the next step for you now to develop this?
I think the next step for us is, first of all, to make some form of basic DOE, try to map out cable types that the nuclear power plants are using, which type of segment of cable types are viable for the nuclear power plants to be investigated, and what is essentially within the scope of the sensor to do. And then the next phase is to then we're actually having dialogues now with Habia Cables, which is one of the suppliers to the nuclear power plants, to support us in this field also with regards to the cables, to essentially make a prototype that we can try in the field and try to support the nuclear power plants as much as possible.
And would that include this, as you mentioned, this sort of horseshoe?
Indeed, that's our aim. So we have some ideas, and I think that one thing that we need to do is to have a dialogue with the teams in the nuclear power plants, for instance, the operators, what is most convenient for those guys. So they're the end users essentially. So we need to get some input from them.
Thank you. Does anyone else have any questions for Payam? Please raise your hand. Mohit, please.
Yes. Hello. Do you hear me, Payam?
Yes, loud and clear.
If I understood correctly, your NMR technique, do you have some plans to look at it, that how small change can you see from this technique? Like, for example, could you see some changes where you do the aging at lower temperatures?
Well, it hasn't been on the agenda yet, but essentially it would be possible, since the benefit with the NMR sensor is essentially the sensor that we used, essentially per minute we were making 300 scans. So you can make a series of scans and just collect data. So if you have the time and resources, and if you can make a low temperature aging and then have the sensor available, it could be essentially a long-term aging you can do and just collect data and then use that also to model the performance of your rubber.
Perhaps I was thinking that we can couple these two experiments together, like same time we can do both things, microcalorimeter, and we can put somehow your device in the microcalorimeter and look at what results are coming from NMR.
Absolutely, we can have a chat about it in the sidelines, and also you're collaborating with Michael, so I'm also doing the same, so we could just get connected and have a discussion about that.
Great, thank you. Any other questions for Payam? Okay, so thank you very much then.
Thank you very much.
And moving on to the final presentation for today, which is evaluation of phenomena observed during accelerated aging of cable insulations. And this will be provided by Trevor Toll from AMS in the US. Hi, Trevor, nice to see you.
You too, Monica. Thank you very much. Let me just try to share my screen real quick. All right, can everyone see the first slide?
Yes, thank you.
Okay, excellent. As Monica mentioned, my name is Trevor Toll. I'm the lead engineer for the Materials Testing Laboratory at Analysis and Measurement Services Corporation. We're a US-based company in Knoxville, Tennessee. So nothing too exotic. But what we do, our whole company, what we do is we provide INC testing, instrumentation control system, and sensor testing for nuclear power plants. That's what our core competency is. From a materials testing standpoint, we do what we actually specialize in is aging and obsolescence testing of components in industrial applications. So we look at predominantly nuclear power plant cable insulation polymers. So we look at aging there. We also do specialized electrical testing of cables in situ to actually look for issues, not just in the insulation, but also in connectors and in devices and things like that. So a lot of different technologies, a lot of different techniques we use, but from a material standpoint, we're really focused on aging. We've done testing for nuclear, U.S.-based nuclear power plants. We've also done international plants, and we've done testing for outside of nuclear power for all kinds of different industries, looking at aging of electrical cables and components. So my presentation today is entitled Evaluation of Phenomena Observed During Accelerated Aging of Cable Installations. It actually kind of goes hand in hand with what's the previous presentation by Payam. So hopefully this kind of builds on a little bit of that from how we're handling it. I really want to focus on the types of things we've observed under our conditions, under our accelerated aging conditions, in the polymers we've tested, and then how we're actually dealing with them, trying to understand them and try to account for them in our data. Won't spend too much time on the introduction. Everybody kind of knows these, the first few slides. Basically, why are we concerned with cable aging in general, or aging of polymeric components, or any components in general? Because the current fleet of worldwide nuclear reactors is getting older. They're aging. Of the 400, this is data, the plot I show on the screen is data taken from the IEA PRIS database in November 2021. Of the 442 worldwide nuclear reactors currently in operation, many of them, most of them are 30 years or older. That's what the plot is actually showing, is the age of the reactors over up to 50 or 60 years essentially. And then the net electrical capacity, what's actually produced by these different reactors, and the size of the bubble in each case represents how many reactors are actually that age. So you can see there's a high concentration of reactors over 30 years old. In the US, a lot of plants are getting to the end of their initial license, period. They're entering periods of continued operation of license renewal, and a lot of plants are looking to go even further than that, operating from 60 to 80s and subsequent license renewal periods. And then there's been even talk of people trying to push, in the US anyway, push these reactor ages maybe into even 100 years of operation, which is, going to be challenging. But we'll see what happens there. But anyway, the point is, why we're worried about it, why we're worried about cable aging in general, or aging of any structures, systems, and components and critical assets, is because things are getting older. Our work has predominantly focused on aging and degradation in cable insulation polymers, looking at ways to basically looking at developing techniques and tools you could actually use to do assessments of those, and actually provide valuable information on the condition of cables to the plants. So how do we actually address cable insulation aging? Basically, the approach many have taken, and most everyone has taken, is implementing cable condition assessment and monitoring tools. So not just ways to assess the insulation, but also ways to test for issues in electrical circuits, like component problems like connectors, end devices, things like that. So what I show here is not by any means comprehensive, as based on the last presentation. There are other techniques. I don't list NMR here, but there's a lot of different methods out there that can be used for aging evaluations and condition assessments. So from an electrical testing standpoint, reflectometry best techniques like time domain reflectometry, insulation resistance, and then like impedance measurements. We use those a lot of times to assess the overall health of a circuit, looking at, is there anything electrically, a problem, like trying to identify bad connections, trying to identify issues, like I said, in end devices, and those types of things. We also employ techniques like frequency domain reflectometry and dielectric spectroscopy, which are electrical tests that are specifically sensitive to changes that occur in the electrical permittivity of insulation polymers as a result of aging and thermal oxidative degradation or radiation-induced degradation. So those are the types of things types of tests we can employ. There's also a wide range of mechanical, thermal, and chemical testing techniques. Elongation at break, sort of an industry standard technique, tensile test, Denner modulus, looking at changes in hardness of polymers, oxidation induction type measurements. Won't go through them all. Everyone's familiar with these types of techniques, but the reason why so many techniques are employed, which and have been studied over the years, is that there's really a wide range of methods that can be used. And honestly, there's no silver bullet, is like we like to say. There's not one technique that applies to all insulation materials, all types of cables, all constructions. You really can't just use one technique and decide that's all I need to do to address these problems. So we employ a wide range of tests and techniques, and we offer that to do specialized condition, or basically do condition assessments of cables. And so these are the types of tests we actually have been using that have been developed both by, through our work, but also through international studies. We were a part of an IEA coordinated research project several years ago that looked at a lot of these techniques and looking at, what materials are these applicable to. That was actually led up by us and several other different international representatives. The technical work was actually led by Dr. Subernay. But we looked at a lot of different techniques. We looked at a lot of different methods. We looked at what techniques actually work with different types of materials. So a lot of work has gone into developing these techniques, and a lot of work continues to develop tools for these applications. So when we're developing these tools, as was mentioned in the previous presentation, we basically make an assumption that we can do accelerated aging studies, use higher temperatures above 100 degrees Celsius, say, for most materials, or even higher in a lot of cases, and basically say the properties of those insulations and the characteristics and data we're going to get at those accelerated aging temperatures reflect what's going to happen in the natural aging environment. So that's the kind of the assumption that we make. Again, that has to be taken with a grain of salt, and I'll kind of talk about that in the next couple of slides. But that's the general approach. We say that polymers, and in general, it's true over a fairly somewhat wide temperature ranges. Polymers follow, time temperature superposition properties. A lot of the properties that, the polymers will follow those relationships, especially mechanical properties. And so again, we can use data taken at higher temperatures or higher levels of, stress, and use that to reflect surface environment degradation. And so that's what we actually employ for condition monitoring, the tool development generally. And basically, we'll go through a full accelerated aging study. We'll look at all kinds of different cables and insulation polymers. We'll do periodic testing using the techniques I showed in the previous slide, and we'll look at how those properties of the insulation and the cable itself change with increasing levels of degradation. And basically what you see in the photos is just a few of the aging facilities we have here at AMS, and the different configurations for different types of materials we test and different types of cables. So again, and it was mentioned in the previous presentation, you have to take the accelerated aging data, its relationship to in-service conditions, with a grain of salt, because there can be substantial differences depending on your aging condition and the type of material you're dealing with and the cable. There can be substantial differences in what happens under accelerated aging conditions and what happens to the material under natural aging conditions. There can be differences in material chemistry. There can be differences in aging characteristics and proper processes, and in turn, because of all these different, kinetic differences, reaction mechanism differences, the polymer will have different property, potentially have different characteristics and properties. So just a couple of examples of aging phenomena that might affect the polymer degradation process in materials. Inverse temperature effects, which are really prominent in semicrystalline materials aged, subjected to aging under radiation conditions at lower temperatures. So we have a lot of chain scissioning reactions that are going on in that case, and they actually induce a lot of degradation from that regard. And then you also have to look into sequential versus simultaneous aging effects, which is something we're looking at both in our project, but also looking at other work and trying to compare results from our project we have right now with people with the Nuclear Regulatory Commission of the United States. They have a project where they're actually doing simultaneous aging. We're actually doing sequential radiation, then thermal aging in one of our research efforts. And And the differences there can be, you know, mechanistic, you know, are you actually, what kind of changes are you inducing in the material and its chemistry and structure? And then how does that, what, you know, depending on what process you use, whether you do radiation, then thermal, or thermal radiation, sorry. Or if you do, you know, any kind of combination or sequential or simultaneous thermal and radiation, what kind of different aging effects are you going to get? Variations in activation energy, obviously, you know, we've kind of shown a little bit, but once you get outside of a certain temperature range, where it's low or high end, you will, you know, during the aging process, oxidation wise, thermal degradation wise, a lot of materials, most materials will exhibit differences in activation energies outside of a certain temperature range. So we have to look at those variations, especially when you're looking at accelerated aging versus in-plant aging, natural aging conditions. Copper catalytic effects, which is something that we've had to deal with, and I'll talk about that in a little bit, but basically it's at elevated temperatures, we see interactions between the basically a conductor and the insulation polymer, which has you know, implications on our electrical data, and then things like inhomogeneous aging effects like diffusion limited oxidation. And this is just a few examples of the types of things that could happen, but it's really just trying to summarize the different types of aging processes that might take, you know, the simplistic idea of accelerated aging from, you know, okay, we have a simple aging process, but it makes it much more complex and complicated, and you have to actually go in and try to figure out what's actually happening to the materials. So the work we're doing, basically to develop condition monitoring tools and in essence, look at these different aging effects, because we have to develop these CM techniques to compare data between tests. We've done testing and are continuing to do testing at a wide range of temperatures. We're doing thermal only exposure of a lot of polymers at 120 degrees Celsius, 110, 130, 135. We're doing high temperature materials like ETFE, ethylene tetrafluoroethylene, PEEK, and polyamides and silicon rubber at higher temperatures, thermal only temperatures at 190 Celsius. And then, as I mentioned, we have a project going on right now where we're looking at conducting sequential radiation, then thermal exposures of a few different materials, including cross-linked polyethylene, cross-linked polyolefins, ethylene propylene rubber, and a few. A lot of the cables we have are jacketed with hypalon or chlorinated polyethylene. And in the sequential radiation and thermal studies, what we're doing is we will initially do a radiation exposure at about 25 kilorad per hour, up to a lifetime dose of 30 megarads. So that's what we're actually using as our gamma lifetime dose is 30 megarads. And then we'll do a thermal exposure at 120C for the XLP, EPR, XLPO materials. We're also doing silicon rubber in this program. And we do that aging thermally at 165 Celsius. And then at different points in that aging process, we're actually taking cables and samples out of the ovens at different points in the aging of the process of the materials of the cables, and then we actually send it off and do a LOCA exposure, loss of coolant accident exposure, design basis event test. And so in that case, we're subjecting it to 150 megarads of post-accident gamma radiation dose at 600 kilorad per hour, 90 megarads for silicon rubber, and then we're actually doing a LOCA in the process of doing a LOCA, basically pressure temperature profile, essentially. So that's kind of the process we're doing. The reason we're doing that is we're trying to develop acceptance criteria for these different tests that I showed previously, condition monitoring tools. We really want to have, ideally, we will have some results that actually say, okay, these are the properties of these different types of materials when they actually will not do what they're supposed to do anymore for a safety relay cable that's you know, whether it'll pass a LOCA or not, or design basis event or not. Like I said, we're doing a lot of different materials in the different programs we've done. We've done XLP, XLPO, EPDM, EPR, different hypalon, CSPE, CPE, and then on PVC, polyvinyl chloride materials, and polyamides like Captain as well. So we've done a lot, and the reason I show that right now is that I'm gonna show some results from all these different projects, the different things we've seen. So to characterize and quantify the aging phenomena, I mentioned things like, diffusion limit oxidation, copper catalytic effects. We've employed very similarly to the previous presentation was shown just a little bit ago. We use profiling techniques, basically cross-sectional analysis techniques, actually looking at different depth profiles of the materials, looking at, from the outside surface to the middle to the interior where the insulation is in contact with the conductor, if it's aged in that configuration. We're looking at all kinds of different data to understand, okay, what does the material look like holistically? What does it actually look like? How is it aging? Is it inhomogeneous? Is it homogeneous? What kind of different effects are going on? The types of techniques we've used to actually look at these types of aging issues include optical microscopy, so just general visual inspections, trying to look at discoloration, carbonyl index using Fourier transform infrared spectroscopy, and then scanning electron microscopy with energy dispersive X-ray spectroscopy analysis. We're looking at distribution of different elements, oxygen, and in some cases copper if there's interactions, and I'll show some of those results in a second. The data on the left just shows how we actually do the carbonyl calculations. So we take the peak area of the CH peaks around 29, the peak max around 2,900, 2848 wave numbers, and then we basically integrate that, take the area of those peaks, and use it to normalize the carbonyl region, which is around 1750 down to a little lower, a little less than 1800, which you see in the plot there. So the blue in this case is a baseline data. The red represents an age sample, and you can actually see the differences in the peak amplitudes and the peak areas you see here. And that's how we actually define it, taking the carbonyl peak area ratio of the carbonyl area peak area to the CH peak area. And then we also, like I said, employ SEM EDS analysis. That's what we see in the bottom screen. That's just an SEM image, but we actually go through the cross section of the insulation and look at the distribution of different elements in the material. And so I'm going to get into the types of things we've seen in our data, which wasn't really surprising given the temperatures we're at in a lot of cases, especially with diffusion limit oxidation and inhomogeneous aging effects. The types of DLO things, these are basically some of the DLO results and the things we're doing to understand and basically account for the impact of DLO. So diffusion limit oxidation, as was mentioned earlier in the day, is basically the material, insulation material will consume the free oxygen that's available for diffusion at its surfaces, and it'll prevent it from penetrating, and it won't be able to diffuse to the interior surface. So you'll end up with degraded surfaces of the insulation, but relatively non-degraded oxidized material toward the middle of the material. So what we see here are profiles. We've taken SEM EDS data showing oxygen profiles we've taken from a cross-linked polyethylene aged to 3,000 hours at 120C. You can see the distribution of oxygen based on atomic concentration. The orange plot on the left, in the left plot, shows the baseline distribution of oxygen through this sample. The blue plot represents what the oxygen profile in the polymer looks like after 3,000 hours at 120 Celsius. And in the optical image you can see on the left, you can actually see the discoloration, which you expect is indicative of diffusion limit oxidation. You can see the darker edges around the surfaces of the material, the outside and interior surfaces, and then the lighter region in the middle, indicating we have inhomogeneous aging effects going on. Similarly, I didn't mention this before, we are aging a lot of different sample types. The reason is because we're looking at a lot of aging effects, and we're looking at a lot of condition monitoring tools. So we're actually doing different types of samples. So our type 1s are samples for the future slides I'm going to show. The type 1s are insulations aged with no conductor, no jacketing, just bare insulations in the ovens. The sample type 2s are basically 8 to 12 inch, what we call whole samples, or basically just sections of cable. that are aged in the normal cable configuration. And what we'll do is remove the jacket at different points in the aging process. We'll take these out. We'll cut the jacket off to remove the different filler different components in the cable, and then test the insulation. These are capped with silicone rubber caps to help prevent oxidation at the ends of the cables, but we do try to sample toward the middle, away from the edges. The reason we're doing these is we're trying to relate the type 1s to the type 3s, which are these longer, 25 feet or more of cables. We're actually doing things like reflectometry and dielectric spectroscopy on to assess, in situ electrical techniques and how effective they are. So we're trying to relate type 1, type 2s, and type 3s materials, to each other, and they're each going to, based on the data we've gotten, they're each going to show different aging effects and mechanisms and things like that. And we're really trying to understand the differences we see there. So those are the type 1s, 2s, and 3s that I mentioned. So the data I show on the left is a type 1 material. So that's just a bare insulation aged in the oven. A type 2 on the right is one of the samples. See the same type of discoloration pattern, although the middle set, the lighter region is whiter in that one, indicating potentially more, significant diffusion limit oxidation effects and homogeneous aging effects. And there's a difference in the in oxygen profile. You can see, you still see that parabolic relationship, but keep in mind that because of oxygen consumption by the jacket material, we're actually seeing more significant inhomogeneous aging effects from an oxidation standpoint in these materials because the amount of oxygen getting to the insulation through the jacket and other components in the cable is limited. So that's the idea behind the type 1s. Type 1s have DLO effects, but type 2s and type 3s may have even more significant inhomogeneous effects. In our radiation and thermal studies we're doing right now, we're doing FTIR profiling. So we're actually doing microtoming through the insulation. The XLPs, this is an across-linked polyethylene at different thermal aging hours. And the circles, or the data points you see at the top, are actually carbonyl index values calculated using from the exterior surface of the material, so the one that's in direct contact with the aging environment, closest to the aging environment. And then the triangles you see are actually the data carbonyl index values calculated at the middle of the material, so the most significantly affected regions in terms of diffusion limit oxidation effects. And you can see there's a pretty big difference throughout the aging process up to 4,407 hours in the exterior surface oxidation or carbonyl index levels and the middle of sample. So the levels of oxidation are substantially different. We're trying to profile that and understand it and hopefully account for it in our data. This is another example of the same diffusion limit oxidation effects we're seeing. We're looking at high polon here in EPR. So this is a dual layer insulation with a EPR base layer with a CSP jacket material or overlaying material essentially bonded to it. You can see the oxygen profile from the EDS scan. You have one level of oxygen at one, and this is data taken at 120 degrees C after 1,065 hours of aging. You can see the oxygen profile, the differences you see in the levels of oxidation and the oxygen profiles in the two different materials in this insulation. You see the high polon has much higher. So again, that in this case, the EPR we've noticed is very affected because of the DLO effects we see. And in this case, we have DLO effects, again, in type 1s is just the DLO effects from the normal insulation, but we also have inhomogeneous aging effects from in the type 2s and type 3s from the jacket consumption of the oxygen and everything like that. And that's what we actually see in the carbonyl index values in the bottom plot. So the left is the high polon data we've taken. The blue data represents the type 1 insulation, so the bare materials. The green data represents the type 2 data taken for the high polon exterior layer. And so you can see how different the oxidation rate essentially, or the carbonyl index value, is changing over time in the two different sample types. Similarly, you can actually see the EPR when it starts finally changing in the type 1 material, when and you can see its oxidation levels or carbonyl index changes are significantly behind the hypalon layer because of DLO effects in the type 1s, but also the EPR in the type 2s and 3s are represented by the green data points. There's been very little change in carbonyl index or levels of oxidation observed in those materials up to 2,745 hours. So these are the kind of differences we've observed in the materials and the different types of aging phenomena and effects we've seen from a diffusion limited oxidation standpoint. Another phenomenon we've observed is copper catalytic effects. So what happens here is actually because you're getting oxidation and essentially of the copper during the aging process, also you're getting copper diffusion and copper ion diffusion into the material at the insulation conductor interface. And that actually catalyzes the oxidation process of the material at that surface. And so that's what you see, the black region that develops, all this blackening. That's a direct result of the copper catalytic of reactions going on at the interior surface of the insulation. And you can see how it progressively worsens with increasing aging time. This data is taken at 120 degrees Celsius. And so you can actually see this is some on the left is some the discoloration we've seen in cross-linked polyolefin insulation, both at the exterior surface but also at the interior surface where that copper catalytic reaction is happening. And then in the bottom right corner of the screen is actually XLPE sample type 2 insulation we've tested at 2,000 hours after 100 or after 2,000 hours of aging at 120 degrees Celsius. In the EDS data, you can actually see that at that interior surface, you are getting copper migration into the insulation that's driving interaction. And then the left image actually is an insulation tube that was pulled in tension to do tensile testing. You can actually see the cracks that formed at that interior surface because of that catalyzed oxidation process that's happening. Inverse temperature effects wise, because we are doing sequential radiation, then thermal, and we are doing radiation at lower temperatures, we did have significant inverse temperature effects in a lot of our samples under the current program we have. Basically, that process is you have a lot of gamma ray radiation at the lower temperatures, induces a lot of chain scissioning and free radical formation. But in our process, once you heat it up and go through an annealing process, essentially a thermal annealing process, you get cross-linking. You do have to do that in oxygen. You can't do that in a nitrogen environment. It is the cross-linking you see is driven by oxygen, oxygen being available for the material, so the recovery you're going to get. So what happens is the chain scissioning induces severe decreases in mechanical properties, tensile elongation properties, essentially decreases the toughness of the material, but the cross-linking actually recovers a lot of those mechanical properties over time. So what I'm showing, yeah, I'm sorry.
2 minutes left.
2 minutes, okay. I'll go quicker. So all I show in this plot is just the DTA or DSC's scans I've got for the material. The polymer chain cross-linking process does happen because able to recover because you get these lower temperature mobility crystalline regions that actually allow the chain to actually, when you heat it up at the aging temperatures, to go through the cross-linking process. So now I want to get into the effects of some of the polymer of these things on the polymer properties we have, we've seen. So when we did EAB testing or elongation break tensile testing of the type 2 samples, the insulations from whole samples, we initially thought, okay, diffusion limit oxidation effects, that they will age slower, the EAB will decrease slower than the type 1s. But that did not happen. That's not what we observed. We actually observed the orange traces is the decrease we saw in the type 2s. And the blue is the type 1s. We've seen an XLP and EPR. Basically, what actually happened is the type 2s actually decreased faster or at the same rate, essentially, the EAB wise, as the type 1s. The reason for that, after doing analysis, is we think is because of the copper catalytic effects that are going on, the surface effects that are going on. So EAB is generally really affected by surface oxidation. It's a technique that is very affected by surface conditions because of that copper catalytic effect and the surface reactions going on. We did not see the DLO effects we were thinking we would see. We actually saw either an opposite or basically the opposite. Type 2s decrease faster than type 1s. However, in oxidation induction measurements like OIT and OITP, we did see the expected DLO effects. We saw that the type 2s were actually aging slower. The OIT, OITP values were aging slower, or a slower rate than the type 1s, which is what we would expect to see. So what are the implications on electrical data? So we've got our type 1s and type 2s. We got two tests that show different things. So obviously, the type 3s are going to be affected by DLO. They're going to be affected by these different aging phenomena. So what if we were to do EAB and we said, okay, this material, this EPR right here fails at 4,000 hours, we'll say 50% EAB is a conservative end of life condition. That's just for an example in this case. But we don't see any changes in electrical data. So it's really important that you understand what is going on in the materials, what the data is actually telling you. If you're going to take EAB, you really need to understand, okay, do I have diffusion limit oxidation effects? Do I have all these inhomogeneous aging effects? And how do I relate that to my electrical data? And so we're actually looking at ways to account for that. This is just interesting stuff we've seen for inverse temperature effects. It has major implications on polymer properties. You can see from baseline, this XLP sample, semi-crystalline sample, has this huge decrease in EAB, but a huge amount of recovery after 168 hours of thermal annealing at 120 C. Interestingly, we saw the same result, similar behavior in our oxidation induction time and temperature measurements. And some of our electrical results also showed that too, where you actually get this decrease, recovery, and then more of a typical OIT, OITP decreased behavior you would expect. And so this is what I wanted to address too. So how you've got all these things going on, you have all these aging phenomena. How do you relate your type 1s, your type 2s, your type 3s to each other? How do you relate the condition monitoring results and accelerated aging to each other? What are methods you can actually use when you have all these things going on? So one method we've actually tried out and continue to refine is, okay, we've got our type 1s, which age at a certain rate. And what we actually show here is the type 1 data is the blue. The carbonyl index values for the exterior surface is the blue, and the middle is the orange for the type 1s. That's how the oxidation profiles look with increasing aging time at 130 degrees Celsius. The red is the surface oxidation going on in the type 2s at the exterior surface. So you can see there's a lot of deviation, and it would be expected that, there could be a lot of different surface phenomena, especially when you're aging insulations and cables. The green actually represents data acquired from the middle of the type 2s, and the purple represents data from the middle of the type 3s. So you can see this huge difference in oxidation effects at different aging times for these materials, and how differently they look because of DLO and inhomogeneous oxidation. So one method we've actually done is, and this is actually applied for different ones, if you look at the middle samples, which are, hopefully away from the surfaces, and you don't have these dissimilar material interactions and driving copper catalytic effects or something like that, you do get profiles that match pretty well when you apply superposition principles. So we actually did that for a few of our samples. We were actually superimpose or basically apply shift factor to the orange and green data points, able to actually get them on the same playing field as the purple data point. And doing that, we actually came up with shift factors in that case, or time shift factors essentially. And what we use those for is that, okay, if you take an EAB value of a type 1, how do you relate that to electrical properties of a type 3 or something like that? And if you're just looking at DLO effects, this is one method that we've tried to use. We're still refining it because there are differences you would expect. This is not a tried and true way of doing it, but it is approach we have used for some of our data to relate one type of data to another, one type of material to another. This shows the application of that for oxidation induction temperature measurements. So the blue is the type 1 data, the orange is the type 2. And then using one of the shift factors we actually came up with doing this method, where we're able to apply that, and you can see it superimposes over each other. So we're able to kind of account for the DLO delay using this superposition, kind of approach. We're still going through these types of things. We have ongoing research right now where we are doing the sequential aging studies and LOCA testing. We're trying to develop acceptance criteria, but we're also trying to say, okay, what are the aging processes that are going to induce failures in these different insulation polymers at the different conditions we're at? Is it mostly, we're hoping that it's, we're thinking that it, in the end, the degradation process that will induce failure will hopefully be oxidation related. That way we can relate this, it's still relatable to the in-service conditions. But we are trying to look and say, okay, how do these different effects play into each other? That's part of the research, and that's ongoing. We're actually completing that in the middle of next year. So the summary of what we found, everything we've been testing at the conditions we're at, depending on the sample type and material, exhibited some type of accelerated aging phenomena. Degradation characteristics really varied depending on sample configuration, material type, and cable construction. You can see how these different phenomena had a significant impact on material properties and CM test results, and each different type of CM test exhibited different responses. And we've also looked into methods for understanding and accounting for, using profiling and looking at material evaluations of relating and accounting for, the implications and the impact of aging phenomena on polymer properties and relating one set of data to another. It is important to know that these types of things must be addressed or at least understood during an accelerated aging program. Otherwise, you're going to get data that it's very hard to interpret, especially for electrical measurements that are, can be very impacted by these types of things when you have, trying to do a measurement of something that's highly affected by aging phenomena. So that's the end of my presentation. Sorry for going over. I'll take any questions.
Thank you very much, Trevor. And if anyone have any questions to Trevor, please raise your hand, and we can just stay on after we have finalized the the seminar, because I know that some of you have buses to catch, etc. So just, yes, I see we have one hand. So Trevor, please stay on until I've said goodbye to the other ones. So thank you very much for today, and I hope to see you again tomorrow. We will start at 8:30 CET. And tomorrow we have 2 themes. It's case studies performed with sealants in real nuclear power plant service conditions, and condition monitoring and quality control. So stay on if you want to listen to Trevor answering questions, or if you have questions to Trevor. Otherwise, see you tomorrow. Bye-bye. So please, Maria.
Yes, thank you. Maria Ekelund here from working as a polymer specialist at Westinghouse in Sweden. Trevor, I have a question for you. Did you do any considerations regarding the dose rate effects? Because you have been testing a lot of different polymeric materials. Did you consider the rate and what it would affect the different polymeric materials?
Yes, those are implications that we also want to look into. I was just giving, obviously, I just wanted to give examples of types of things we've looked into, because obviously a lot of different phenomena can happen under the conditions we're at. But what we're trying to do in the end is say, okay, what is the major implications of these different things on the polymer properties, and then our resulting condition monitoring data. But that is something that we're taking consideration. This is a lot of especially the sequential aging studies, because a lot of the work we've done prior to our current research has been thermal testing. Over the last almost 3 years now, we've conducted that sequential radiation and thermal program. And we are still completing that result. We're going to look at the local results, and then we're going to actually see, okay, this is the different types of data we got. We're doing a lot of different tests. And then we're going to say, okay, this is what we actually saw and what actually induced failures and what the properties of the materials were.
Okay, so just a follow-up question. You said you used a 25 kilo rad per hour, right?
That's correct. Yeah.
So how did you choose this rate?
So we actually chose the 30 megarad. That was actually first. That was the lifetime dose that we decided on, and that's based on some work EPRI did for profiling. And then basically just needed to fit that into the radiation levels we were actually, or the time frame for the radiation we did. So we actually did that radiation exposure at Pacific Northwest National Laboratory. And so we have 40 different cable samples. So that's the big 11, in this case, they're 11 feet long. But we have hundreds of different samples. So we had to, our project was now 3-year duration. It was 2-year. We actually got it extended from a time standpoint. But we were trying to make sure we had enough time to do the radiation exposure, then do the thermal exposure, and then do the LOCA. So really the dose rate was decided on based on, all right, we're shooting to have a 30 megarad total dose. And this is the amount of time we have to do it. All these samples.
Okay. Okay, thank you for answering.
It's a very complex area, and I know that Subhané has been thinking a lot about this.
Yes. Yeah, she has worked with us in the past. She's actually been to our company a few times and has talked to us about, you know, the types of things you see in these things and how do you actually interpret the results.
Are there any other questions for Trevor? No, nothing.
Yeah.
No, here's a question. Sten-Olof?
Just probably a remark that this 30 megarad is very, very high level of operation dose.
Yeah.
Like at least compared to what we have in the Swedish and Finnish reactors. There are difficult to find spots that we have
That
so
high.
high radiation. So
Yeah, like I said, this came from some work EPRI, the Electric Power Research Institute in the U.S. did. I think it is a conservative value. Obviously, it's much higher than most things we'll see during operation. The lifetime, though, for most things, is probably much lower.
it's probably 100 times more than we could find in our reactors. So,
Right.
yes, just a remark.
No, I understand. Thank you.
Any other questions or comments? No, it doesn't seem so. So thank you very much then, Trevor, and have a nice day to all of you that are in the US, and have a nice evening to all of you who are in Europe. And I hope to see many of you tomorrow morning again. Bye-bye.
Thank you.
Thank you very much.
Thank you.
Tomorrow.
Thank you, Ray.
Thank you. Bye-bye.
Bye-bye.